How is it that these complex objects, which have nucleons orbiting 10 to the 21 times per second, filling 60% of the volume, interacting with at least two forces, how can these nuclei exhibit such astonishingly simple patterns of regularities? And it's in this area that Franco's contribution really stands out. These themes of complexity and simplicity have been used to describe nuclear structure in a number of major documents around the world in the last years, and I only mention a few that quickly came to mind. The 2007 U.S. Long Range Plan, NUPEC Long Range Plans, 2 National Academy reports, and others. And this is not chance. It's not chance that this idea of simplicity in nuclei and analyzing the simple patterns and trying to understand them is one of the 2 overarching themes used to describe nuclear structure. It owes very, very much to the work and insights of Franco in promulgating the ideas of symmetries and simple patterns in nuclei for decades. Many scientists do nice work. I can look around the room and see a lot of it. It's rare to find one who defines and transforms an entire field, and who basically does it with a pencil. So that's my comment on Franco. I want to just comment briefly on how I met Franco, how I met the IBA and how I met Franco. And we've talked a lot about mentoring and inspiration from people, but serendipity plays a big role too. The reason I got involved in all of this is because I arrived at a party in 1974 5 minutes late. And there was an APS meeting. I got to a party 5 minutes late. There was no place to sit down. And so I sat down on the floor next to Fred Bernthal. I don't know if anybody remembers that name. He later became head of the NSF. I had some 0+ dates, and I asked him, how would you interpret these? Is the Kumar Beranger approach something that would be useful? And he looked at me astonished and said, what? You haven't heard about this new model that was just announced in Amsterdam a month ago? And I hadn't heard of it. And I was so embarrassed that I went back and found out about it. And so a lot of what's happened in my career since then is due to arriving at that party 5 minutes late. Okay, this is back to that slide. And what I want to talk about is linking these 2 perspectives. In particular, talking about the drivers of collectivity and coherence in nuclei, and in particular, the proton-neutron interaction. So I want to spend a couple minutes just reminding you of how important this is and some of its manifestations. This figure is well known to almost everybody here. It shows the energy of the first 2+ state. It shows the energy of the first 2+ state against neutron number in the tin region. And what you see is that these 2+ states are constant for tin, where there are no magic protons. I mean, there are no valence protons. As soon as you get valence protons and neutrons, collectivity and coherence develop. You can see this in another way, and this illustrates one of my favorite themes, that looking at data from different perspectives can often tell you things that you don't get from one perspective. This is the ratio R42, which is the ratio of the energy of the first 4+ state to the first 2+ state. In a vibrator, it's about 2, and in a rotor, it's about 3.33. And if you look in the rare earth region, you see this behavior. And what do you see here? You see the onset of deformation, right? Okay. If you look at the same data plotted against proton number instead of neutron number, you see something not different, but more. First of all, you see the onset of deformation. Here are values near 2, and here are values near 3.33. However, you also see that it's a phase transition. You see these concave curves for neutron numbers 84, 86, 88, and convex for 90, 92, 94, 96. You also see, remembering that R42 is a small value near magic nuclei, that Z equals 64 is essentially magic for these low neutron numbers. And the proton number 64 becomes near mid-shell for higher neutron numbers. So what you see is that this phase transition is mediated by a change in shell structure, and that shell structure is driven by the PN interaction. So looking at things from different perspectives can often be pretty useful. Okay, so I want to talk about proton-neutron interactions, and you can measure these, and I'm not going to go into details on this, but you can measure them empirically with a double difference of 4 binding energies. And if anybody wants to come back to this cartoon later, I can talk about it. Basically, you do a double difference of binding energies, and you extract everything except the average interaction of the last 2 protons with the last 2 neutrons. There can be some other higher order effects, but that's the basic idea. This is what that data looks like over the entire nuclear chart. And what you see, this is neutron number. And you see these spikes here, and you see a little glitch there. These spikes all occur for n equals z nuclei. And these are very strong delta VPN, PN interactions. It's always convenient, at least I find it, to have big numbers go up rather than down. So I changed the sign here, and the sign will be changed in all the other plots. So large values will be up on the plots. So these are these n equals z nuclei. We'll come back to them in a minute. This was the data in 1990 in the lead region, those few points. Since then, a lot more masses have been measured, and now the data looks like this. It's a really beautiful pattern. And you can understand this quite simply in a very qualitative way, and it's the following. Consider a proton and a neutron shell. The order of the shell model orbits, at least the normal parity ones, is not random in a shell. They go from high J, low principal quantum number, to low J, high principal quantum number. So if the protons and neutrons are in similar orbits, you should have large proton-neutron interactions. That would mean large values on this plot. So let's look at how that works out. I need to point at the computer. So this region of large values has Z less than 82 and N less than 126. So both the protons and neutrons are at the end of the shell. They're in similar orbits, high overlaps, large values. These values here correspond to neutrons below the closed shell, protons above, very different orbits, small values. This range of high values corresponds to both protons and neutrons above the magic numbers. So again, similar orbits, large overlaps, large proton-neutron interactions. There's one region missing, you can see, and that would correspond to protons below the closed shell and neutrons above. This is lead here. That would correspond to the next point, and we would expect that to be a small value, namely down here somewhere, that was recently measured, and indeed, it comes down. So you can understand, at least in a hand-waving way, some of these proton-neutron interactions. This is another way of looking at the same data. It's an NZ plot for the entire 50 to 82 proton shell, 82 to 126 neutron shell. And the color coding is such that red values are large and blue values are small. And you notice very significant trends. When protons and neutrons are filling the same quadrant, holes, particles or holes, you have large values. You also have large values along the diagonal. And that makes sense in terms of this picture. Along the diagonal, the protons and neutrons are filling similar orbits, and so you should have the largest interactions. Okay, I'm going to skip this. This has to do with some density functional calculations that reproduce these delta VPN values pretty well, but that's really off the topic. Okay, I want to come back to the Wigner effect. These are delta VPN values in light n equals z nuclei. And there are double difference of binding energies. You can argue whether or not they're solely the proton-neutron interaction. But whatever the case is, you get these huge spikes. These are MEV spikes that occur for n equals z nuclei. Now, what happens in heavy nuclei? Well, in heavy nuclei, first of all, n equals z nuclei don't exist, so that's a little bit of a problem. Secondly, Coulomb force, spin-orbit forces should destroy any remnants of SU4 symmetry, and so you wouldn't expect to see anything, I would think. When we, by the way, the we is Burju Chakirli, the next speaker, and me and our colleagues. When we looked at the rare earth region, we found the following. These are delta VPN values in the rare earth region. And what you see is a series of peaks, okay, which march up in neutron number as Z marches up. And so for each one of these elements, in some cases the data don't necessarily show that there's a peak yet. New measurements are being called for. But what you see is peaks in these delta VPN values for certain neutron and proton numbers. Which neutron and proton numbers are they? Those peaks occur for the number of valence nucleons approximately equal to the number of valence protons. And if you think about filling of similar orbits, you can already see that qualitatively that makes sense. That's for even nuclei. What about for odd nuclei? Same thing. You have these peaks I'll just click here. You again get peaks for n valence equals z valence. You can also, by the way, see the effects of pairing in these oscillations here. When you have odd nuclei, you get higher peaks. When you have odd-even nuclei, the values are smaller because in the even type of nucleon, the orbit occupations are spread out due to pairing, and so you don't have the same enhancements. So what's going on? Why do we see these peaks for n valence equals z valence? So let's consider the orbits in the Nielsen picture. And here I highlight 3 or 4 of them. How much time do I have, Pete? Well, you're going to use it all up figuring it out. Okay, thank you. So these are 4 nuclei with peaks in delta VPN. These are the orbits involved in those nuclei, the last filled orbits. And if you look carefully, they all have a characteristic. Namely, oh, sorry, I jumped ahead. Let me show you this first. Here's the Nielsen diagram, and this red case is here, the green case is here, that applies to 2 of them, and the blue case is here. You can see that in each case, the orbits with the same color have very similar properties. Their shapes are similar. If they have 2 curvatures, like this one, they have 2 curvatures in the other. One comes from the unique parity orbit, and they have very similar characteristics. And what are those characteristics? Namely, the Nielsen quantum numbers differ by 0 and k, 1, 1, 0. So the principal quantum number differs by 1, the z quantum number differs by 1, lambda is the same. Now if you think about that for 2 seconds, if n and nz differ by 1, then since n is nx plus ny plus nz, that means the number of quanta in the xy direction is conserved. And so that means that these sister orbits differ only by a single quantum in the z direction. That's what we call this z quantum transformation. And so they're very closely related. One would expect that they would have large spatial overlap and perhaps large proton-neutron interactions. We've been working with Dennis Benatzos and his student Sofia Karampaggia, and they've calculated overlaps of the squares of these, some of these Nielsen wave functions. And I give you just a couple of examples. And I'm sorry these figures aren't oriented in exactly the right way to see it, but you can still see the point. This is the 1/2 5-2-1 orbit. This is the z direction. This is the rho direction. And here's the 1/2 4-1-1 orbit. Clearly they differ by 0, 1, 1, 0, and they have an overlap of 0.8. Here's another example. This is the 1/2 6-3-1 orbit and the 1/2 3-0-1 orbit. They differ by 0, 3, 3, 0, and you can see clearly just looking at them that their overlaps are going to be smaller. And in fact, the overlap is considerably smaller. If you look at all the orbits, at least the ones with delta k equals 0, you can make a plot of this probability product against the sum of delta n sub z and delta nx plus delta ny. And what you see is that the larger this sum is, the smaller the overlaps. So what we're interested in is the case where delta n sub z equals 1 and delta nx plus ny equals 0. That's this case. These bars represent the range of overlaps for these 35 cases. So this contains about 20 cases, I guess, and they range over these values. Most of them are right about here. But let's look at the composition of these. This has two types of cases. One is delta n sub z equals 1, which means delta nx and delta ny are 0, which means that corresponds to the 0, 1, 1, 0 case, and indeed the overlaps are high. The other contribution to this are cases where delta nx plus delta ny is 1, okay, and delta nz is 0. Those are absolutely irrelevant for these nuclei, because if you look at the Nielsen diagram, you will find that those combinations occur only in very neutron-rich nuclei. And you'll see that in a second. So in practice, the highest overlaps occur for exactly our case of 0, 1, 1, 0 Nielsen orbit pairs. Now, there's another feature of this. If you look at a Nielsen diagram, we have tried to color code this in a way, and obviously you can't follow all of it. But the idea is we've taken orbits here which are related, proton and neutron orbits by 0, 1, 1, 0, and given them the same color. And so if you look through the diagram, you can see that not only are there all these pairs of 0, 1, 1, 0, but they fill in almost exactly the same sequence. So as you go through the shell, a shell of protons and a shell of neutrons with similar numbers of valence particles, you're continually populating orbits that have this highly overlapping relationship.